Yeah, so my name's Thomas Brown. Thanks for coming to listen to me today. I'm going to be giving you a short overview of the Skarv flexible riser system and a briefing on the integrity management strategy that we manage the riser system with. So, for those of you that haven't heard about Skarv before, it was discovered in 1998. Subsea installation commenced 2008. The FPSO was on station August 2011, and first production commenced in December 2012. Production capacity is about 90 million standard meters cubed of gas a day via the Åsgard transportation system, and 85,000 barrels of oil a day at maximum rate via shuttle tanker. The water depth varies 350 to 450 meters. We've got 50 mooring lines in 3 sectors of 5 template manifolds, 16 wells, 42 kilometers of infield flow line, a mixture of corrosion-resistant alloy and carbon steel, 80 kilometers of gas export pipeline, 2 dynamic umbilicals, 1 direct electric heating riser, that's a first for BP, and the reason I'm here to speak to you today, the 10 dynamic monobore risers, of which we've got 2 8-inch production, 5 10-inch production, 1 10-inch gas injection, and 2 12-inch gas export. This is an overview of the FPSO field layout. As I mentioned, 3 sectors of moorings, and in between those 3 sectors, we have 3 sectors of risers, each comprising dynamic umbilicals, monobore, and DH. We've got risers off to the north going to Skarv Atilia, to the west to Skarv BC, and to the east towards Eden. It's worth noting the area under the FPSO is free of subsea infrastructure to reduce risk of any dropped object impacts, and where we have infrastructure going under the mooring lines, we've rock dumped to offer additional protection. Onwards to riser installation. In 2009, we commenced riser installation. We pre-installed 26 riser anchors on the seabed, suction cans, 13 horizontal anchors, 13 vertical anchors. In 2010, we came along and we pre-installed all 13 risers on the seabed prior to FPSO arrival, with all the jewellery installed on the risers, with the exception of the topsides hang-off system. In 2011, once the FPSO was on station, we pulled 3 of the risers into the FPSO, and when the weather window closed, we were forced to wait until 2012. When the weather windows reopened, we pulled the remaining 10 into the FPSO. The pre-installation was selected because it was calculated to give us some installation flexibility, potentially taking 6 weeks off the critical path towards first hydrocarbons. Not all of that was realized in the end from factors outside of the subsea perspective. But in the picture on the bottom right-hand side, you can see the Scandi ACG cross-hauling one of the risers towards the FPSO and one of the heading control tugs on the back, providing heading control backup should one of Skarv's 5 thrusters fail. This is the riser configuration pre and post FPSO arrival. So on the top left, you can see the mooring lines laid out on the seabed and the risers folded back on themselves with the buoyancy modules installed. On the right-hand side, you can see Technip's pliant wave configuration, 43 buoyancy modules giving us that shape. And if we click this link, we can watch the installation process from pre-installation phase to the hung-off phase. So in plan view here, going into a side view, so the Scandi ACG recovering the riser off the seabed, picking it up until the sag bend begins to come off the seabed, and then the pliant wave is rotated 180 degrees around itself, rotating around the vertical anchor, so that we can cross-haul it to the FPSO. And it's worth noting that if we put a clockwise rotation on it in 2010, then we'd be putting an anti-clockwise rotation on it now to ensure that we had no torsion left in the product. So the rotation's just about to take place. Going around. Ready for connection to the riser pulling wire and the final cross-haul to commence. So a brief comment on the riser design. Our riser design was based on our operating experience from west of Shetland. The graph on the bottom left-hand side of the screen is the position of the Skarv products circled in red versus industry experience in 2007. And the gas injection riser is right on the limit of industry experience at that point in time in terms of ID versus pressure comparison. Another interesting point to note, on the right-hand side, you can see a connection between the riser and the riser jumper. So we implemented this into the design. This is just after the horizontal anchor on the static portion on the seabed, because we expected if we're going to have any damage, it's going to be during the tie-in phase of the product into the subsea structures. And if we did damage the product, we didn't want the dynamic riser portion of the annulus to flood. So by putting this inline connection, we can segregate the annulus between the portion that's most liable to be damaged versus the more sensitive dynamic portion. In addition, it gives us the benefit of being able to fit all the products onto transportation reels. So, onto our integrity management strategy, the Skarv Flexible Pipe IMS. It's a risk-based approach, again based on our West of Shetland experience. And the IMS is to ensure that the risers operated within the design intent, whilst allowing the actual accumulated riser design life to be continuously assessed against the theoretical design life. The activities that I'm going to speak about in the subsequent slides is annual and longer term activities, intermittent activities, continuous activities, procedural control, design verification, and spares management. So, firstly, the annual and longer term activities. Visual and CP inspection, we do this on an annual basis of the high criticality areas. You can see an image on the right-hand side of us performing a bend stiffener inspection. We then perform a full-length GVI on a rolling multi-year basis, but the most critical areas we visit on an annual basis. We also perform annual annulus vacuum testing. We do this on an annual basis, and we're looking at a comparison of internal volumes, theoretical versus FAT, post-installation, first year of production, and so on. We have a vacuum test manifold. You can see it on the bottom left image there. And we also perform coupon analysis, which is due to commence in the second year of production. So that's next year. We'll be starting to take our coupons out of coupon holders and doing analysis on that. Intermittent activities, we perform bore fluid sampling, so looking for CO2, H2S, pH, and water cut. We perform annulus sampling. I'll talk a little bit about that on the following slide. And we also perform bend stiffener inspection. So we perform this after every extreme weather event. We have a camera that we can deploy from the FPSO. You can see it on the right-hand image there. It's got its own dedicated eye tubes for inspection. And the idea for this is that you can perform a visual inspection of the riser bend stiffeners immediately after an extreme weather event and decouple the need to find an inspection vessel and also allow a quicker response and a more close-up inspection. Continuous activities. So on the right-hand side of the screen, you can see our vent gas monitoring system. We have one of these on each of our monobore risers. And what we do with this is we perform continuous annulus flow rates with results available on the FPSO and on shore. We perform real-time pressure monitoring of the annulus. We take gas samples from the annulus on a 3-monthly basis, and we take the condensed fluids out of the water trap on a monthly basis. And the reason for that is to, again, we can analyze the condensed water and also ensure that we don't get any ice plugs forming and lock pressure into the annulus. So it's worth mentioning, by putting this VGM in the system, we introduced a risk of essentially blocking a clear flow path out of the annulus and therefore an overpressurization risk of the outer sheath of the riser. So we put this system to a rigorous HAZOP and implemented a number of design changes and risk mitigations to make this as low as reasonably practical on the risk perspective. We also perform online sand detection and metering and online temperature and pressure monitoring, both at the FPSO topsides end and at the subsea structure end. On the bottom left-hand side of the screen, you can see an example of pressure and temperature trace for one of our risers at a given point in time. And from this, we can do analytical degradation of the pressure sheath calculations. Additional continuous activities, environmental monitoring and logging. So this video on the left-hand side of the screen is taken during Berit at the end of 2011. It doesn't look too bad, but it's worth remembering the FPSO is 300 meters long and 50 meters wide, and it is moving around quite a bit. The environmental logging we're recording wave data, FPSO motion response, FPSO excursion, and it's worth noting that the design is verified for ALS conditions, 100-year storm, 100 meters offset. On the right-hand side, the top right, you can see a trace of significant wave height in the field at a given point in time. In addition, that's available to our installation vessels in the field. So if they're not equipped with wave radar, they can also get real-time weather data from the FPSO. And on the bottom right-hand side, you can see FPSO excursion throughout 2013 plotted, with each of the different colors representing a given month. So a number of data points versus the mean datum position of the FPSO. We monitor for fishing activity. These are two examples of quarterly results. Skarv's in about the middle of the screen. There's no significant fishing activity around Skarv, but there is fishing activity within the area. The risers are obviously protected because they're within the FPSO exclusion zone, but this does feed into the integrity management strategy of our flexible jumpers on the seabed, our flow lines, and our subsea structures. In terms of procedural control, we've got rigid procedures in place with the CCR to ensure that the risers are depressurized at an acceptable rate so that we don't induce a carcass collapse. We've verified that with Technique, the manufacturer, and we have essentially limited depressurization phases, then a limited hold period, and then we can continue with depressurization. And that mitigates the risk. We also govern dropped objects and riser protection. So we had a subsea protection strategy, which was created to dictate the protection requirements of our subsea equipment. We have a simultaneous operations manual, which was created to minimize the risk and consequence of dropped objects. We have dropped object reporting. We also have riser protection. You can see it here in the image on the bottom right with yellow. And in those areas, we have DuraGuard fitted to the risers. And we've fitted it in those areas because those are the areas at the most at risk of contact or abrasion. So there's the touchdown point. There's the sag bend, which, as you saw in the animation, is dragged along the seabed for a portion of the crosshaul phase. We did pre-surveys to look for boulders, but you can never know what's just below the surface, so we put DuraGuard on at that position. And also up at the top side ends near the risers, near the bend stiffeners, where analysis showed that in extreme weather events, there's a potential of riser clashing. So we put on the additional riser protection there. It's also worth noting that during the delivery phase, we performed dropped object testing on our flexible jumpers to test against drop mooring on the jumpers from the FPSO or a drill rig, and we had good results back. Performed dissection of the products, and the conclusion, whilst we didn't do a pressure test, was that it would have survived the dropped object event. Design verification. You've probably all heard about flip or flow-induced pulsation. This was been brought up on Skarv a long time ago, and we have performed detailed analysis to understand the flip risk on Skarv. And it's just applicable to our gas risers, the dry gas risers, that's injection and export. At the design phase, we engaged a contractor, and they recommended modifications to make the pipework more robust to a flip and the associated fatigue that could occur. We then tested this on site with response testing. And then during the ramp-up phase, from when Skarv first came online in December last year, every time we've ramped up the export rate or the injection rate to an as yet unproven level, we've had live continuous monitoring, both topsides and subsea, to ascertain that our small bore pipework was not getting fatigued as a result of flip. This was just concluded a couple of weeks ago. We've now gone through the full export and injection envelope rates, and we've confirmed that we have not had any pipework response as a result of flip. In fact, we're not even convinced that flip is occurring, but we're certainly not seeing any pipework response. On the pictures here, you can see a subsea basket on our export riser base, which is what the vessels were monitoring live vibrations via, and you can see one of the clamps on the small bore pipework. In addition, as a risk mitigation, we're putting in a pressure pulsation monitoring system in 2014, and that's going to be mounted on the FPSO, and it's going to give a real-time indication to the control room if flip is occurring. So regardless of whether we would have piping vibrations if flip occurred, we would have a warning that flip has onset, and then we can take risk mitigations to assess that, see if we need to limit our envelope or make modifications to our operating conditions. Sparing philosophy. We have a spare gas injection riser. This was procured by Skarv, along with all the associated riser jewellery. It was selected on a number of factors, basically the replacement delivery lead time, the number of base case installed risers, and the economic impact of losing gas injection service. It's also worth noting that the gas injection riser via a adapter flange could be used in export service as well, so it could be used to replace a gas export riser. The primary reason for replacement would have been seawater ingress into the annulus, and we've performed service life assessment on the risers, and we've calculated that for the most sensitive riser, the gas injection riser, we could have approximately 4 years before service life would begin to be exceeded. So with our annulus vacuum testing campaign, we'd pick it up, and then we'd be able to engineer and execute riser replacement before we'd have to shut that riser down and replace it. On to the conclusions. What would BP have done differently if the original Skarv design was revisited? And from my perspective, I think it would have been beneficial if we've had a riser bend stiffener monitoring system online, providing real-time data incorporated into the original turret design. So you can always come back and retrofit this system, but it's never going to be as good as having a system that's designed into the turret. So that's a lesson learned for our team. The Skarv flexible riser system, to summarize, is managed via our comprehensive IMS. We've had no anomalies found to date. We get quarterly and annual assessments provided for our review. We update our IMS as required, and we've got a robust system in place to manage the ongoing integrity of the Skarv riser system. Thank you very much. Any questions?
Okay, any questions to Thomas?
Charles White, BG Canard Development. 2 questions related to the vent gas monitoring. One is the gas that's coming out of that. I understand you're measuring the flow rate coming out of the annulus, but where did that gas go?
It's vented to a safe location on top of the turret, so it's not going to the flare system, but it's to a vent on top of the turret.
Okay. And then all this data that you're collecting from that,
Yes.
both the gas side and the water side, what do you do with that data?
In terms of the flow rate, that's logged, and then it's taken, given to our integrity management contractor, and then they're monitoring riser performance and getting cumulative gas rate from the annulus over a period of time over the design life for the risers, so that we can watch for any trends that develop. It could give you an early warning of a flooded annulus before you come and do your vacuum testing, or it could give you an indication that your VGM system isn't working and you need to investigate it to ensure that you're not going to cause a plug in the annulus vent system.
And are you sharing any of that data outside of BP?
We haven't done as of yet, no. We haven't had any requests to, and we haven't as of yet.
Thank you.
Any more questions at the back there?
Hi, Vish from Shell in Aberdeen. I've got a question on the temperature and pressure monitoring. You mentioned like you've been doing that. Have you incorporated any of those fiber optics? Or?
No, we haven't incorporated that in the design. So for the, it's just topsides monitoring and then it's subsea monitoring. And for the case of the production risers, we don't have monitoring at the riser base, so it's monitoring at the manifold, which is 3, 5, and 13 kilometers away, depending on which manifold you're talking about. So it's not giving you exact temperature profiling through the riser, no.
Okay, thank you.
Hi, Torgrim Andersen, Kongsberg Gas. Did you guys consider a smoothbore riser?
It was considered, especially it's come back again and again for the flip risk, but the conclusion now is that we should have potentially gone for, to mitigate the risk that we've been dealing with over the last year, one of the export risers being rough bore, one of them being smooth bore, as a quick way to respond to a flip occurrence risk. But I believe that it was viewed as being more of a technology stretch at that point in time, and we went for a rough bore.
Thank you.
Thank you, Jan Muren for Subsea. What's the reasoning behind missing the inclusion of the bend stiffener monitoring system? I find that a little bit odd. I've seen a few bend stiffeners failing, but it shouldn't.
Yes, well, it was discussed during the design phase of the FPSO, and the conclusion that was made by a number of groups was that the spyball camera system that we deployed down would be a sufficient risk mitigation. And with the mitigations that we have in place within the IMS, I think we're well covered, but I think it'd be a much more belt and braces solution to have the sonar system as well. It's worth noting that we are field trialing a sonar system at the moment, primarily for monitoring the integrity of the mooring system, but it's not out of the realms of imagination to see that extending on to being able to monitor riser bend stiffener excursion, and then or riser excursion at a given depth just below the bend stiffeners. And if that excursion was to suddenly begin to increase, you could make a conclusion that there's a problem with the bend stiffener and perform an inspection and any mitigation measures as required.
Okay, any more questions? One at the front here.
Hi, Xavier Hordo, Subsea 7. I'm not an expert in annulus, but you said that you are monitoring the flow of gas in the annulus.
Mm-hmm.
So are you 100% sure that there is never any gas pocket in the catenary?
Gas pockets. Well, the whole annulus is gas filled.
Yeah.
So.
But you are controlling the flow at topside and subsea end, isn't it?
It's plugged subsea, and it's open. It's essentially open to vent topsides, and we have a piston in place that shuttles backwards and forwards and monitors gas flow as a result of piston movements in a given volume.
Only at the end fittings.
Sorry?
Only at the end fittings then.
Yes, on the riser end fittings. There's one located right next door to each riser topside end fitting. Yep.
Okay, thanks.
And what's the response you have in the procedures for the different measurements?
For which different measurements? So if we're going to get a high pressure alarm on the annulus pressure, we have a high alarm and we have a high pressure alarm. If the high alarm sounds, then it's to go out to the turret and confirm that all the valves are configured correctly in the vent gas monitoring panel. And then if the high alarm sounds, which is half of the nominal rated pressure of the outer sheath, then we take a decision to shut down the riser immediately, reduce any further gas diffusion through the riser, and then allow a more detailed investigation to take place. And that's alarmed in the control room, and it's alarmed to my mobile phone as well.